Hello, hi everybody. Salut, JB Morin.
Salut, buongiorno.
Now, Christian, maybe, hey, ciao, Christian.
Hello.
Nice to see you all. I am here with Professor Di Prampero, JB Morin, and Christian Osniak. Okay, so I will start with Professor Di Prampero, so you can introduce our guest.
Well, I don't have much to say because JB Morin, il est bien connu dans le domaine de la physiologie de l'exercice musculaire. He's very well known in his field, but I like to remember the time was quite a few years ago when Jean-Benoît Morin and a young colleague of him, they were both young in those days. I also was younger. Karim Zameziati spent a few months in the Department of Physiology in Udine because they were attending a PhD course which was co-organized, organisé en co-tutelle, between the University of Saint-Étienne and the University of Udine, and our friendship and knowledge and the basic construction of our ideas dates back to those days. And today we will hear what this beautiful idea of studying the relationship between maximal acceleration as a function of the speed, the running speed from which the acceleration itself is started. It's a beautiful idea that emerged in Jean-Benoît head some time ago, and he is the main responsible for this beautiful idea that we are trying to apply more broadly nowadays. Thank you, Gibito, for being with us, and I hope we'll have some time to see personally and drink a couple of wine together.
Yes, merci beaucoup, Professore. It's always a pleasure to see you physically or via the web. And yes, it was always good to have a few drinks and share ideas on the paper. And I'm very happy to share some new ideas here to everybody. So thank you for inviting me. I must declare that I have no conflict of interest with gpexe, and I was not paid to do this talk. So the only conflict of interest I have is friendship and sharing ideas. So I hope this is still okay. So basically, I'm gonna explain where we are now, and I guess most of you are now familiar with the concept of force, velocity, and power profile. It came from the idea of seeing sprint acceleration through a macroscopic view, and this was taught to us by Professor Di Prampero and also by people in the biomechanics like Robert Alexander. And the principle is to say, when you analyze something that's so complex, you want to address first with simple models just to see what are the features that are responsible for the main effect. And the main effect in sport is performance. And in sprinting, it's displacement as a function of time. So the force velocity profile has been there for years. And very simply, the model starts from velocity as a function of time. And using basic Newton's kinetics laws of motion, we can address the force as a function of the velocity, where force is the ground reaction force in the horizontal direction during the acceleration. So basically, we use that in football. Many other people use it. We also use it in rugby. You just need to measure the speed. And some other applications have been published recently and used in training, for example, in hockey, but also in US football. And basically, I won't go into the details, but you go from assessing the player's capability, monitoring their rehabilitation, monitoring their season, the effects of training, the effect of fatigue, etc., etc. And we are now even asking the question of, is it relevant in prevention and in rehabilitation? So if you want to have full details on the existing body of literature, you can go to my website where there's all the papers accessible, and of course some blog posts where I detail other research. So the overall idea is that if you measure performance only, you have a very low level of information. Because here, for example, you have two players with the same performance on a 30-meter, and they have very different force and velocity profile, and they have very different mechanical outputs. So it means if you want to go deeper into the determinants of performance individually, you have to analyze the profile a bit more, let's say, in deep. So to do that, you have two possibilities. One is to use a sprint instrumented treadmill, but that's very, very rare. The other one is to use the reference method in biomechanics, that is force plates, but there's only 2 or 3 places in the world where you can do that. And so because this was very frustrating, we try to have the idea of a simple field method. So to come with this field method, we simply analyzed the literature, and we saw that people very early, so Archibald Hill was in the 90s, so almost 1 century ago, people observed that when a sprinter, a player, accelerates from 0 to top speed, the speed increases in a very simple exponential function. So this has been observed systematically. And here, this is the beautiful work of the team of Archibald Hill. So it was the Nobel Prize some years ago. And so you see that the mustache is related to a very high level of science in physiology. And this was also repeated in the field, as you see here. So this was 100 years ago. And this was also repeated in the 70s. So this was the technique of a Russian team of researchers. They attached a wire to the sprinter to have the speed time analysis. And of course, every time we measured this in sprinters, in football players, you see this is the world record by Usain Bolt. This is my son when he was only 3. This is a very old master sprinter. Systematically, this exponential increase in speed was observed. So on that basis, Pierre Samozino, who is listening this evening, salut Pierre, proposed a method where we start from the velocity as a function of time, and we use Newtonian dynamics to estimate the propulsive power, the propulsive force in the horizontal direction. Very simply, the force is proportional to the mass of the body and the acceleration. So when you know the speed or the velocity, you know the acceleration, and it's easy to compute. So here, we validated that method, first in 2016, second last year, and last year we used a single sprint because in Japan, the researcher Ryu Nagahara is very fortunate because he has a 50-meter force plate system. So we compared our model estimations to the real reference force plate data. And as you can see here, the method is pretty accurate in estimating the force. And you can see here in the square, the horizontal force output over time versus every single step on the platform. And all you need is body mass, running speed, or running time. So the method is reliable. And in practice, you need to ask the players to sprint. So this is a test up to their maximum speed, and you need to measure their speed or their displacement. So we published some free spreadsheets where you can do the computations based on the split times or the speed. Typically, the device you will use is a timing gate, a radar gun. But recently, and this was published today, Mathieu Lacombe and his colleagues showed that basically you can do that computation using GPS. Basically, GPS devices today have about 20 informations per second, and it's accurate enough to quantify the acceleration correctly. So a few applications in training and injury management. There has been a lot of works using that method to try and interpret every player's profile and the training content that we can adjust to the players. So the question is, how should I train the player as a function of their force velocity spectrum? Another type of application is injuries. And for example, this profile has been used in hamstring injury management. The first step is, if you monitor the player's profile, you can adjust the training load as a function of what they need, and maybe a better training load management is related to a better prevention. I love this paper where colleagues in prevention say the key concept of monitoring training load for injury prevention is to adjust the load to the players to minimize the risk. So I would say that knowing the profile of the players will help the staff better consider the needs, the individual needs of the players. Now, if the players get injured and you go to the return to sport process, we worked with Jordan Mendigucha in Spain to use the profile for the return to sport. So in this very first study, we observed that when they returned to sport after hamstring injury, football players had a lower maximum power and a lower maximum force. We call that F0. But at the same time, they had the same maximum velocity. And the surprising result was that 2 months later, all the values were back to normal. So it means that the force velocity profile was modified after rehabilitation. And in a second study, it's a case study, we showed that exactly the same. When the player was back to training after rehabilitation, his sprint profile was not the same. As you can see here, his maximum force output was lower. So basically what I want to point here is that the force velocity profile is a useful tool in the toolbox to guide the sprint specific return to performance process. An example here, this rugby player in a club we are collaborating with. The first 2 lines are 2 tests before a big hamstring injury. And the last line is the first test after we got some normal values. So basically the rehabilitation was over and we said, okay, let's test you. The result of the profile F0, V0 were not okay. So he did an additional session or cycle of rehabilitation. And when the test was okay, we were back to the reference profile and we said, for us, he's ready to go. So he missed a few more games, but he did not have a re-injury. Okay, so this is an example of use in professional sports. So time to play. The idea here is that we are going to present today the in situ profile. And basically the in situ profile came to our mind because when we talk about the lab and the field, people very often complain that to get the force velocity information, we need to do a specific sprint test. So as you know, all the models are wrong. Some are useful, and we think that the force velocity models are useful. And the main limitation from our practice in football is that when you do a test, you bring a stress. And it's always stressful to test the players. So the big question is, how can we get some information without specifically testing a maximum sprint? So I'm going to explain you briefly the ideas, and we are now validating the method. First, you need GPS data, all the data, everything. All the sessions, all the football sessions. You can also add game data. And when you have all the data, like you have here, if you watch the graph, this is 2 weeks in a professional football player with 20 Hertz measurements. So it means every single point here is an acceleration velocity point. So when you run on the field and you want to pass the ball or you want to attack, every 20 hertz, we have some points here. And what you observe here is a cloud of points, all the speeds and the corresponding acceleration. So it means sometimes you run slow and you accelerate a lot. Sometimes you run fast and you cannot accelerate a lot. And this is the basic data. So we did not test the players. We just followed their GPS data. The second step is that for each speed that you see throughout the range, from 3 meters per second to the maximum speed, what was the maximum acceleration produced? So again, we don't know when it was produced. We just know we have a point of maximum acceleration at every single speed. And as you know, when you run fast, you cannot accelerate a lot, and vice versa. So this is the maximum acceleration zone you see here in red, from the maximum acceleration points on the left to the maximum speed on the right. Okay? When you have that, you plot the speed maximum acceleration regression, and you have a line that's very, very highly linear. And this line is what we call the acceleration speed profile. And then you can compute the variables that are A0, which is the theoretical maximum acceleration. That's your maximum capability. S0, which is your maximum theoretical running speed. And of course, the orientation of the profile, which is the slope, the incline of the profile. What you need to understand is that this profile is the limitation of the physical capability of this player in football. There is no sprint test. It is not linear sprinting. That's real life football. So here we have the same player, but during the week, the coaches ask them to do a 30-meter sprint test. And the 30-meter sprint test data are highlighted in black. You see what I mean? So on the left, in situ data, on the right, in situ data, and among them, a test. All right? So this is the basic idea. We take what you produced as a football player, and we analyze your maximum capabilities. Of course, we cannot accelerate maximally at every speed. Otherwise, football would be an incredible game, but we are limited as humans. So here, in this example, we have a full week, 2 weeks, sorry, of data, 7 sessions. So every session is here, 1, 2, 3, 4, 5. The coach was asking different things. You see that the shape of the points is a bit different. In some sessions, there's a lot of maximum speed. In some sessions, there are not, because the topic of the session was different. And then when you take all this data and you cumulate them, you have the 2-week in situ profile. So on the left, you have a 30-meter test. This is only for one player. And on the right, you have 2 weeks of football practice. So this idea basically came from cycling, because you all know that football is good, but cycling is definitely the best sport. And this was published by Frédéric Grapp and Julien Pinot a few years ago. You have also the same models with power, time, duration in running, like Thibaut and Perronnet models. And basically here, they collect all the power data in training, during the races, everything. And so they don't test the cyclists. They just take the power values and they can build the record power over time. Because if you do the Tour de France, you will have some maximum power over very short periods, like a sprint. You will have some maximum power over 3 or 5 minutes. You will have some maximum power over 30 minutes. And so you can build the athlete's individual record profile. So the idea maybe was influenced here for us. Now, everybody has in mind the comparison. What are the similarities and differences between the classic force velocity and the in situ acceleration speed profile. First, the force velocity is a test. You need one linear sprint. So we could say it's semi-specific. It is not football, but it is sprinting. And the in situ just needs football data, good GPS data. We say a minimum of 6 sessions, okay? But it includes all types of movements, and it is very football specific. You cannot be more specific, okay? It was during football. So here, just the computation. Why do we say force velocity and acceleration speed? Just because to know the maximum force, you need to quantify the air friction. And it's pretty easy during a single test, and it's not easy at all during 2 weeks of football. So this is why we use A0. But as you can see here on the left, conceptually, when you express them in the same units, F0 and A0 are the same variable. It's your maximum force or the associated acceleration. And as you can see here, the air friction doesn't change much the story, but still, it is not exactly the same. So, as Einstein would say, you just count what counts for you. If you want to know the maximum sprint test capability, do a test. If you want to know the football acceleration profile, do a specific football acceleration profile. But for now, and this is the preliminary results I'm presenting you, so it is data in progress. I would say that you don't want to analyze one profile from the other. It seems to be two quite different information. So the result that we had on 16 pro players, the linear acceleration speed profile is very, very high quality of linear fitting. You need at least 6 sessions of data to be sure to have every maximum acceleration throughout the speed spectrum. We have a pretty good inter-period reliability. So basically, we compare 2 weeks of training to 2 weeks of training just after. And so the statistics are pretty good. And as you can see here, this is for one player, the in situ profile for 2 weeks before a sprint test, and the in situ profile for 2 weeks after the sprint test. So of course, they are not exactly the same, because the 2 weeks of football were not exactly the same, and the player himself was not exactly the same physically. But still, we have very close data. So now the funny thing is that, and this is why you need a little of wine or spumante, you answer some questions and many other questions come to mind. Is it reliable? As I said, we are doing the stats right now. How does it change with fatigue? Will I see the players changing with fatigue their acceleration speed profile? Does it change when you do small-sided games, depending on the side of the games, depending on the tactics? How does it change during the season? Is it different between players? Is it different between the positions? Some positions may have different acceleration speed profile than others. Does it change with tactical periodization? Does it change with the playing style? If you are Jurgen Klopp or if you're another coach, do the players have different profiles when they play with you as a coach? Does it change after training blocks, after detraining? Does it change post-injury? Well, many questions. We are first giving the method, validating the method, and then, as I said before, for everybody, it's going to be time to play and time to observe, and this is what is very exciting. So I want to thank the team because it's a very exciting teamwork. So you can see here during one of our high-profile meeting, myself, Professor Di Prampero, Christian, Pierre Samosino, and Yann Lemat, who is the young boy digging into the data with us. So thank you, everybody, and hope you enjoy and have questions.